Hello everyone. Welcome to video lecture series of communication engineering. In this lecture, we'll discuss double sideband suppressed carrier, that is DSB-SC, and single sideband suppressed carrier, Ssbsc. In this, I'm going to talk about double sideband suppressed carrier derivation, waveform, bandwidth requirement, frequency spectrum, power calculation, and generation of DSB-SC signals. Under single sideband suppressed carrier, we are going to see the bandwidth requirement of Ssb Sc system, its frequency spectrum, output voltage and power calculation, generation of Ssb Sc signals. Let us begin the session with DSB-SC. First, we'll discuss the drawbacks of double sideband full carrier, that is conventional amplitude modulation scheme. It has three terms, namely carrier, upper sideband USB, and lower sideband LSB. We know that the carrier signal does not carry any information. So most of the power is wasted by the carrier transmission. This problem is overcome by suppressing the carrier signal. As we discussed earlier, most of the power is transmitted in the carrier, but it is not used for carrying any information. So this carrier signal can be suppressed and only sidebands can be transmitted. Such type of modulation is called as DSB-SC, double sideband suppressed carrier. In DSB-SC system contains only lower sideband and upper sideband terms only. Let us discuss the mathematical derivation for this double sideband suppressed carrier modulated signal. The carrier signal is represented as EC of t. The modulating signal is mathematically represented as EM of t. The double sideband suppressed carrier modulated signal is represented as EDSB-SC of t. Substituting the values of EC of t and EM of t in the modulated signal, will get EM EC cos omega CT into cos omega NG. After using this formula cos A cos B, we'll get the double sideband suppressed carrier modulated signal as EM EC by 2 cos omega C plus omega M of t, which is upper sideband. And another term in the modulated signal is EM EC by 2 cos omega C minus omega M of t, which is nothing but the lower sideband. So from this above equation, we can conclude that this double sideband suppressed carrier will carry only two sidebands and it does not carry any carrier signal. This is the waveform of double sideband suppressed carrier modulator system. The first waveform represents the message signal, that is baseband signal. The second signal represents the DSB-SC signal. Here the envelope contains only the sidebands and the carrier is suppressed. For this system, it requires the bandwidth as that of the conventional AM system, that is bandwidth is equal to 2 into FM, that is where FM is nothing but highest frequency of the modulating signal. Even though we suppress the carrier signal in this modulation technique, but we don't have any change in the bandwidth requirement. This is the frequency spectrum of double sideband suppressed carrier. We can notice that we'll have two sidebands, LSB and USB, and the carrier is suppressed and the bandwidth requirement is given as 2 FM. Next we'll see the power calculation. So in the previous session, we have seen the power calculation for the conventional AM system. It is represented as PT. PT is total power, which is equal to PC carrier power into 1 plus MA squared by 2. And the carrier power is derived as PC is equal to EC squared by 2R. So in this DSB-SC system, the carrier signal is suppressed. So the transmitted power of DSB-SC system can be represented as PT DSB-SC, which comprises of only two powers. One is upper sideband power, PUSB, and another one is the lower sideband power that is represented as PLSB. Substituting the values of upper sideband and lower sideband power, we'll get the total power requirement for the double sideband suppressed carrier, which is given as MA squared by 2 into EC squared by 2R. This can be replaced as PC. So the power saving can be determined by using the formula PT minus PT DSP SC divided by PT. Substituting the values in the above equation, we can get the power saving equation as 1 divided by 1 plus MA squared by 2. Now you consider modulation index MA is equal to 1. So substituting the place of MA is equal to 1, we get percentage of power saving as 66.67%. So from this we can conclude that due to the suppression of the carrier signal, the power is saved up to 66.67% in DSB-SC system. Next, we'll discuss about the generation of DSB-SC. There are two methods to generate the double sideband suppressed carrier signal, namely balanced modulator. And the second scheme is ring modulator or diode balanced modulator. Let us discuss about this balanced modulator. In this balanced modulator, two nonlinear devices are connected in balance mode so that the carrier signal is suppressed. The circuit automatically eliminates the unwanted carrier signal, and we assume that the two transistors are identical and the circuit is symmetrical. Let us discuss the derivation part of this modulator circuit. Here, the input carrier signal is cancelled because two devices are connected in balance mode. So, the two collector currents of the transistors are given as EB1, which is sum of EC plus EM, and EBE2, which is the difference of the carrier signal and modulating signal, that is EC minus EM. The collector current for this modulator is given as IC1 and IC2. Substituting the equations and by using the formula A plus B whole squared and A minus B whole squared formula, we can determine the IC1 and IC2. The output voltage equation E naught is given by the formula E naught is equal to K into IC1 minus IC2. By substituting the values, we'll get the final output voltage of this modulator circuit. So here, the tank circuit is tuned to the carrier frequency, so we can suppress the modulating voltage. So the first term in the above equation is cancelled, and finally we get only one term, that is E naught is equal to 4 into EM EC A to K sin omega MT into sin omega CT. And by using the formula sin A sin B, we can simplify this output voltage equation as E naught is equal to 2 into EM EC A2 into K cos omega C minus omega M of T minus cos omega C plus omega M of T. The first term represents, that is omega C minus omega M represents the lower sideband, and omega C plus omega M represents the upper sideband. Let us discuss the merits and demerits of the system of this type of modulator. It increases the efficiency because of suppressed carrier and power economy is high. Demerits, the bandwidth is same as Dspsc. The design is complex. Applications, cryptography techniques or secret communication, telephony system. Next, we'll discuss the ring modulator or diode balance modulator. Here, this ring modulator suppresses both unwanted message and carrier signal at the output. So the bandpass filter is not used in the ring modulator circuit. The four diodes are controlled by a carrier wave, which is represented as EC of T, the frequency of omega C. It is also called as lattice type balanced modulator. This is the waveform of this type of modulator. The first signal represents the modulating signal. The second signal is the carrier signal. And third signal is the diode signals. And fourth one is the output of the modulator circuit. Let us discuss the operation of this type of modulator. Here the carrier signal is acting as the switching signal, which is used to alter the polarity of the modulating signal at the carrier frequency omega C. Here there are two modes of operation in ring modulator. Let us discuss the two modes. In the first mode, we consider that no modulating signal is applied. So only the carrier signal is present. So during the positive half cycle of the carrier signal, the diode D1 and D2 are forward biased and D3 and D4 are reverse biased. Here the current divides equally in the upper and lower portion of the primary winding of the output transformer and reduce the magnetic field. The magnetic field produces at upper and lower part is equal and opposite. So cancel each other. No output is produced at the secondary winding of the output transformer. So the output voltage is 0. During the negative half cycle of the carrier signal, the diode D3 and D4 are forward biased, that is conducting, whereas D1 and D2 are reverse biased. The current divides and produces the magnetic field at the upper and lower part of the primary winding of the output transformer, which cancels each other, and therefore no output voltage is produced at the secondary winding of the output transformer. So in this case also the output voltage is 0. This is the first mode of operation. Whereas in the second mode, we consider that both carrier and modulating signal are present. So during the positive half cycle of the carrier, diode D1 and D2 are forward biased, whereas D3 and D4 are reverse biased. Here the carrier signal voltage is positive, so it connects the secondary winding of the input transformer to the primary winding of the output transformer. It means that the message signal is available at the output of the secondary winding of the output transformer. That is, output voltage is equal to your modulating signal voltage. In another case, during the negative half cycle of the carrier signal, diode D3 and D4 are forward biased, whereas D1 and D2 are reverse biased. Here the carrier signal voltage is negative, so it connects the secondary winding of the input transformer to the primary winding of the output transformer. The message signal is inverted, so the output voltage at the secondary winding of the output transformer is minus EM of T. Let us discuss the derivation of this type of modulator. The carrier signal and modulating signal mathematical representations given. The output voltage is given by the formula E naught of t is equal to Em of t into Ec of t. Substituting the values of modulating signal and carrier signal, will get the output voltage, and by using the formula sin A sin B, we can simplify the equation, and finally we'll get two terms. The first term represents the lower sideband and the second term represents the upper sideband. Let us discuss the merits and demerits of this modulator. It does not require external power source to activate the diodes. Longer life, demerits, practically it needs maintenance, produce same bandwidth as AM, applications, telephone systems, RF transmissions. Let us discuss about the single sideband suppressed stereo, that is Ssbsc. In Dspsc system, both the sidebands are carrying the same information and the bandwidth is equal to 2 FM, like a conventional AM system. One sideband is sufficient for transmission and reception of the original modulating information. Therefore, one sideband is suppressed in DSB-SC having along with the carrier signal. This type of system having only one sideband and suppressed carrier is called as single sideband suppressed carrier. So here the bandwidth of the system is reduced to half of the DSB-SC system. So the bandwidth requirement for the system is equal to the modulating frequency FM, highest frequency of the modulating signal. This is the pictorial representation of the frequency spectrum of the Ssbse system. So in this spectrum, in this we can observe that we'll have either LSB or USB. The carrier signal, one sideband is suppressed along with the carrier signal. So the bandwidth requirement, which is equal to the highest frequency of the modulating signal. The output voltage equation of Ssbse system is given by the following equation. E naught is equal to Em Ec by 2, that is your suppressed carrier. Then cos omega c minus omega mt, that is your lower sideband frequency. Let us derive the power for this Ssbse system. The total power requirement for this Ssbse is given by the formula 1 by 4 ma squared into Pc. Power saving can be derived by using the formula Ps is equal to Pt minus Pt Ssb Sc divided by Pt. By substituting the values, we can determine the power saving as 4 plus ma squared by 4 plus 2 ma squared. Now you consider ma is equal to 1. So when calculating the percentage of power saving, we get 83.3%. From this, we can conclude that the power is saved up to 83.3%, and it is high compared with the DSB-FC system. Next, we'll discuss about the generation of Ssbse system. There are two methods to generate the single sideband suppressed carrier. The first one is frequency discrimination of filter method. The second method is phase discrimination method. Under that, we'll have two methods. One is phase shift method. The second one is the modified phase shift or Weaver's method. Let us start our discussion with frequency discrimination of filter method. This method involves the generation of DSB-SC signal, then extracting only one sideband using appropriate filter to obtain single sideband suppressed carrier. The block diagram of this method is shown below. Here the modulating signal and carrier signal from low frequency crystal oscillator, which provides both upper sideband and lower sideband, are given to the balanced modulator. The modulation takes place in the balanced modulator. The passband filter is used to reject any one of the sideband of the Ssbse. Here, the attenuation occurs in passband filter or selective filters, and it can be overcome by mechanical or crystal filters. And here the filters operated in the frequency range of 500 kilohertz to 80 megahertz. Let us discuss the advantages of mechanical filters, which is smaller in size and it has very good attenuation characteristics. Crystal filters, it is cheaper, but it works only at frequencies greater than 1 megahertz. Then, single sideband suppressed carrier wave is generated by mixture and linear power amplifiers. The merits of this modulator circuit is attenuate the carrier by sideband filters. The bandwidth is flat and wide. The demerits are it requires mixtures and cannot be used at high and low radio frequencies. The next method is phase discrimination method. Under that, first we'll discuss about phase shift method. Here, the drawbacks of filtering method can be overcome by using phase shift method of generating this Ssbse signal. The principle behind this phase shift method is here the undesired sideband is suppressed, that is removed by generating that same two undesired sidebands which are 180-degree out of phase with each other. Here the two sidebands are added and cancel each other so that one sideband is suppressed and the other sideband is transmitted. Here two balance modulators and two phase shifters are used in this type of modulator circuit. The modulator M1 receives the message signal and 90-degree phase shift of carrier signal, and modulator M2 receives 90-degree phase shift message signal and direct carrier signal. Here two modulators M1 and M2 are constructed so that it should be work in the balance each other. Balance modulator M1 generates upper sideband and lower sideband, both are shifted with 90-degree phase shift. And balance modulator M2 produces USB with 90-degree phase shift and LSB with minus 90-degree phase shift. And these two signals are applied to the summer and filter network. The output of the balance modulators are added by a summer and amplified by the linear amplifier. The signals which are in phase are added and which are out of phase are cancelled each other. Finally, the output of the amplifier network produces only one sideband, that is maybe either upper sideband or lower sideband, and the carrier is already suppressed by balance modulator. Let us discuss the merits and demerits of the system. Low audio modulating frequency are used. Without any filters, it can transfer from one sideband to other. Demerits, distortion occurs due to 90-degree phase shifter. Modulator sensitivity should be equal to baseband signal. The next method is modified phase shift or Weaver's method. It is designed to overcome the drawbacks in phase shift method. Let us discuss the operation of this type of modulator. The modulating signal and carrier signal is applied to the balance modulators M1 and M2 with phase shifter. Here the low pass filter is applied at the output of the balance modulators M1 and M2. Here the low pass filter cutoff frequency is given as input to balance modulators M3 and M4 and its output is added to produce single sideband suppressed carrier signal. This is the block diagram of this modulator. Let us discuss the derivation of this modulator. Here the modulating signal is mathematically represented as Em of t is equal to Em sine omega mt. The audio frequency carrier signal is represented as Ea of t and the RF carrier signal is represented as Ec of t. So here the balance modulator input M1 and M2 are given and the low pass filters 1 and 2 are represented. So the output of the low pass filter 1 is given to the modulator M3 and the output of the low pass filter 2 is given to the modulator 4. We consider that EM and EA is equal to 1. So here the modulator M3, balance modulator M3 and M4 output equations are given. So the output of this M3 and M4 are given to the adder circuit and the output of the adder circuit is represented as E0 of T. Here the balance modulator output M3 and balance modulator output 4 are added up. So finally we'll get E0 of T is equal to 2 cos omega C plus omega A minus omega M of T. This equation is referred as the final RF output frequency, that is Fc plus Fa minus Fm, which is Ssb of the RF carrier, Fc plus Fa. If USB is desired, simply interchange the carrier inputs to balance modulators M3 and M4. Then RF is Fc minus Fa. The advantages of this modulator circuit is switching the sidebands are easy, maintains the correct output. The demerits are extremely complex in circuit design, made whistles at the output. Let us discuss the different types of modulation techniques, that is DSB-FC, DSB-SC and Ssbse. Let us compare all these three techniques. Here in DSB-FC, no sidebands are suppressed. The transmission efficiency is 33.3%. The bandwidth requirement is 2 FM. Here the generation of this DSB-FC is easy and it is mainly used in audio broadcasting. Next, Dspsc. Here only the carrier is suppressed and 2 sidebands are transmitted. 66.6% is its transmission efficiency. The bandwidth is same as that of the Dspsc and the generation is complex and it is mainly used in quadrature multiplexing, short distance point-to-point communication. In Ssbse, carrier signal is suppressed along with one sideband fully and only one sideband is transmitted. It produces the transmission efficiency of 83.3%. The bandwidth requirement is just half of the previous two methods, that is FM. It is very complex in generating the signal and it is mainly used in police wireless communication, mobile, VHF and UHF communication systems. Thanks for watching this video.